Good morning everybody. This is Srinivas Raju, Physics Department, Viveka Degree College, Tuni. I would like to introduce BSc Physics third semester, that is wave optics. In wave optics, for unit 1, aberrations, this topic is new for all the degree second year students, because of in your earlier classes intermediate there is no concept about aberrations, so we need to use not only blackboard, we use PPT presentations and some other things, animations like that. Now I'm using a hyperphysics, so this would be better to understand. It's linked with between so many concepts. So look at this. So look at this, one in a lens concept. Here this is a lens. A lens have a focal length and it has a surface power and it has a magnification, and lens maker formula, and what is positive lens and what is negative lens, and refraction, images are no lens equations, thin lenses, real images and virtual images, ray diagrams, and thick lenses. These stream are not aware of the students. It's beyond our course. Lenses are made with glass and which is affected by aberrations. Here we are. Firstly, I want to explain what is lens. Lens means it is a two curved surface and it is a transparent like glass. So glasses are generally three types: borosilicate glass and crown glass, and some dense barium crown glass and flint glass. Usually the lenses are made with crown glass and flint glasses. What the aberrations? What is the aberrations? Aberration means if there is an object, if we use the lenses, the object, the image of the object is different from the object, because of these defects. Defects are at position of the image, or color of the image, or size of the image. So these defects are called aberrations. Aberrations are mainly divided into spherical aberrations and chromatic aberrations. Chromatic aberrations due to unequal refraction of the colors, and here the spherical aberrations are due to spherical surface of the lens, and the other are coma and astigmatism and curvature of the field and distortion. Chromatic aberrations. What is chromatic aberrations? A lens will not focus different colors in exactly same place. Here it is a lens, a white light passing through the lens, then the light is dispersed into 7 colors, but these colors exactly same place. Here red color is far from the lens, and violet is refract more than it is nearer to the lens. So the image is blurred with colors red to violet. So here the it is a concave lens. Here the light is incident on the concave lens, and it is divergent into violet and red, but the virtual image is placed in front of the concave lens. So here also the image is spread into violet color to red color. So left to right. So here the thin lens, so it's our beyond the class. And what is the focal length? Here, what is the focal length? Focal length means the distance between the center of the lens to image. So here the light is incident on the lens, and it is converge into the some point. The distance in that point, here it is image, a point image. The distance between the point image to the center of the lens is called focal length. Here the focal length 1 by f is equal to power, and concave lens, here this is called as a negative lens, and convex lens is called as a positive lens. So here P is equal to 1 by f, that means lens power. So back to the concept, chromatic aberration. So in chromatic aberration, the light is divided into some of the colors. The image is divided into some of the colors. This chromatic aberration is divided into removed by using a doublet, means a convex lens of crown glass and concave lens of flint glass is the combination of these two removes the chromatic aberration. See here red light and blue light are placed in one place. So this is the one solution, and another solution is achromate doublet. In achromate doublet also a pair of lenses, that is double convex lens with a concave lens is cemented, that means tightly packed. So the light is dispersed with these two. So here the chromatic aberration is removed, that means achromatism. So it's called as achromate doublets. These are the beyond our focus. So now in chromatic aberrations, in spherical aberrations, there is a rays are called the away from the far from the optic axis. This is a principal axis or optic axis. those rays are called marginal rays, and nearer to the principal rays axis is called partial rays. Uh, the marginal rays are converged nearer to the center, and the partial rays are converged in a different point. The partial ray focus, here it is a marginal ray focus. So the image is formed in between the marginal ray focus to partial ray focus. So the distance between the marginal ray focus to partial ray focus is called longitudinal spherical aberrations. And also the image is height also differ, that is called transverse spherical aberrations. That means spherical aberrations are divided into longitudinal spherical aberrations and transverse spherical aberrations. Next, these are we explained in coming class. So we need to understand what is convex lens and what is concave lens. So I want to play an animation. So look at this.
Hi friends, if you place an object like this pencil in front of a convex lens, do you know where the image will be formed?
So this is the
what will be the properties of the image?
convex lens.
Or if we replace it with a concave lens,
So this is
now what is
concave
the
lens.
image going to look like? Actually, I don't need this pencil because in this video,
Oh.
I'm going to be the object. And I'm
Wow.
going to go and stand in front of the convex and concave lens.
He's
And let's
doing
see
great job.
where my image is formed.
He's
I'm
on
going to make the
parallel
topic of
axis.
image formation for spherical lenses really easy for you. And as usual, we'll finish off this video with our top 3 questions on this topic. Remember, we have light ray rules for spherical mirrors, and we use these rules to draw a ray diagram and obtain the image. If you haven't watched my video on spherical mirrors, do check it out.
This is
Similarly,
concave,
we have light ray rules for spherical lenses.
convex is for
In this video, we'll be looking at these
cos.
rules and how to apply them for our ray diagrams. Let's start with the convex lens. The convex lens is a converging lens. For image formation, we need to draw the lens accurately. Let me show you a simple trick for that. Draw a line representing the principal axis.
There is a principal
Mark
axis.
the optical
Pradhana
center
aksha.
O roughly in the center of the line. Using a ruler, mark 2 points to the right of O. F2 is, let's say, at 2 centimeters from O, and 2F2 is double the distance. It's at 4 centimeters from O. Similarly, on the left side, mark F1 and 2F1 using the same distance. O is the optical center of the lens, and F1
Optical center.
and F2 are the 2 principal foci of the lens.
And this
Now
is
draw the
principal
convex lens.
foci.
You can roughly sketch the lens or use a compass to draw the 2 arcs of the convex lens. Make sure that the lens is thin. Don't draw a thick lens. Now let's take a look at the rules for image formation of a convex lens. Light is a very visual topic, so I would suggest you to keep pausing the video and draw the ray diagrams in your notebook. Then you'll get a much better feel of what is going on. There are 3 rules for the convex lens. Rule 1. A ray of light which is parallel to the principal axis, after refraction, passes through the focus on the other side of the lens. Rule 2. A ray of light passing through the optical center of the lens goes straight. It emerges without any deviation. Rule 3. A ray of light passing through the focus after refraction becomes parallel to the principal axis. Let's place the three rules that we have learnt for convex lens on our concept board. Can you see that rule 3 is exactly the opposite of rule 1? It's due to reversibility of light.
3 rules.
Remember, when drawing a ray diagram, you need to draw 2 rays from a point on the object. So you need to choose 2 out of the 3 rules. You can choose any 2 rules that are convenient for your diagram. And as I promised, I'm going to be the object and I'll go and stand in front of the convex lens. And you need to apply these rules and find my image. So let's go ahead and try it out. Here I am on the principal axis.
Okay, that is a principal
I'm far
axis,
away from the convex
on
lens.
The principal axis.
I'm going to walk and stand on different places on the principal axis.
It's a very best animation.
And as you'll see, my image will change based on my position. So let's start with case 1. I'm standing beyond 2f1. You need to consider the rays from the top of the object. So from my head, remember, we need to select 2 out of the 3 rules. Let's use rule 1. The ray which is parallel to the principal axis after refraction by the lens passes through the focus. So this is our first ray here. For the second ray, let's use rule 2.
Another point goes to
the ray which passes through the optical center goes straight through, undeviated. So what does the intersection of these 2 light rays represent?
So image must
That's right,
be
the image. It's the image of my head, the
river.
top of the object.
Yes.
Because we considered the light rays from the top of the object. So where is the feet of my image? It's on the principal axis. So you don't need to draw the light rays for the bottom of the image. Simply extend the top of the image to the principal axis and we get the bottom of the image. So as you can see, we found the position of my image here. What are the properties of an image? There are 3 points to consider here. First, is the image real and inverted or is it virtual and upright? Second, is the image magnified, diminished or is it the same size as the object? And third, what is the position of the image? So what are the properties of the image here for case 1? That's right, the image is real and inverted. It's diminished, and as you can see, the image is formed between f2 and 2f2.
So between
you'll find similar diagrams in your textbook. Of course, I won't be the object there. The object is usually shown with an up arrow,
so
since the object is upright and marked as
image
AB. The image is also shown with an arrow and it's represented as A dash B dash. As you can see, the arrow is inverted here because the image is an inverted image. Now let me walk closer to the lens.
So if
I'm going to stand at 2f1 for our case 2. Once again we need to use 2 out of the 3 rules. For the first ray, let's use rule 1. The ray of light parallel to the principal axis after refraction passes through the focus of the lens. For the second ray, we can use rule 2.
F2.
The ray passing through the optical center of the lens goes straight through, undeviated.
Optical center.
What are the properties of the image here?
Is exactly same
Can
size.
you see the symmetric nature of the diagram?
Here,
I'm standing at 2f1 and my image is formed at 2f2. The image height is the same as the object height. That's my height. And can you see that the image is real and inverted? It's a real image because it's formed by the intersection of the rays. if you try drawing the diagram for this case, you might find that the image is not exactly at 2f2. Now this can happen if your foci f1 and f2 and the points 2f1 and 2f2 are not exactly equidistant from each other, or the rays are not accurately drawn. So to avoid such errors, an important exam tip for this case 2 is to use the cheating trick, which is first draw the image and then you draw the rays. Since we know all the properties of the image, we can easily draw it here. It's a real and inverted image, and this image is going to be exactly at 2f2, and the image height is exactly equal to the object height. So once you've drawn the image, you can go ahead and draw the rays. Now I'm going to move closer to the lens. So we have our case 3 here, where the object is between f1 and 2f1. I would suggest you to pause the video here, draw the ray diagram and try to find the image yourself. Also write down the properties of the image formed. So what's the nature of the image you got? That's right. The correct answer is it's a real and inverted image that's magnified. Here's the ray diagram, and as you can see, the position of the image is beyond 2f2.
the 2f2.
Next, I'll move ahead and stand at the focus of the convex lens.
If he placed at
Again,
f1,
we need to apply 2 out of the 3 rules. This is an interesting case because as you can see, the refracted rays are parallel. The refracted rays never meet. So where is our image formed? The image is far away, formed at infinity. The image is real and inverted, and it's highly magnified. Now let's look at the final case, where I move really close to the lens.
So
the object, that is me, is between the optical center and the focus of the lens. Let's use rule 1 and rule 2 to draw the light rays from the top of the object. As you can see, the refracted rays here are divergent. So we need to produce them backwards
if there is
to
a
obtain
divergent,
our image.
the virtual image
Wow!
is placed
Can you see? The image is
at
magnified
a
here.
point 2f1.
So what are the properties of the image? The image is virtual and erect, it's magnified, and it's formed behind the object. Do you know a use of convex lens
What is
for
the
this
use
case?
of convex lens? It is a
That's right.
magnifier. చూసారండి, మ్యాగ్నిఫైయర్ కింద ఉపయోగపడుతుంది మనకి. సో దిస్ ఈజ్ ద బేసిక్ కాన్సెప్ట్. ఇంతకన్నా ఎక్కువ మనం యానిమేషన్ లెంగ్త్ పెంచితే క్లాసు డిస్టర్బ్ అవుతుంది. సో నెక్స్ట్ క్లాస్లో మనం కాన్కేవ్ లెన్స్లో ఏ విధంగా ఇమేజెస్ ఫామ్ అవుతాయి అనేది నేర్చుకుంటూనే ఇంకా ఫోకల్ లెంగ్త్ గురించి, కాన్వెక్స్ లెన్స్ గురించి, మిగతా వాటి గురించి మనం తెలుసుకుందాం. ఇంట్రడక్షన్ క్లాసెస్ అయితే ఒక 2-3 క్లాసెస్ బేసిక్స్ మీద ఉంటాయి. సో అప్పుడే మనకి లెన్సెస్ గురించి, లేకపోతే ఫోకల్ లెంగ్త్ గురించి, ప్రిన్సిపల్ యాక్సెసెస్ గురించి, వీటి గురించి మనకి పూర్తి అండర్స్టాండింగ్ అనేది వస్తుంది. థ్యాంక్ యూ.